So just one very small exercise, anticipating what I will do later. It's a linear algebra exercise, very simple, but something that at least, okay, when I needed this, I wasn't able to find it in a nice reference. It's about cross product in 3D, okay, vector product. So if you have a matrix A, and you take the vector product of A applied to two different vectors, there's a formula for this in terms of the vector product of U cross V. Okay? Simple exercise. And the formula is that it's the cofactor matrix of A applied to U cross V. So just prove this. It's a simple exercise. But I don't know. I don't think this formula is very well known. Not on my favorite Wikipedia website. Okay, so in today's lecture, I want to essentially redo the computation from yesterday in a slightly different way, and also show how to get a quantitative estimate on the error. Okay, so just to recall the setting, so this is a quantitative version of, let's say, single scale homogenization. So the setup, again, is going to be dt rho plus delta to the 1/2 w. And now let's say we even allow some sort of slow variations. So this is periodic. In this variable, the delta is fixed, and we want to do essentially homogenization with lambda large. Thinking of lambda, but as I said yesterday, we don't want lambda going to infinity because then this would be the wrong scaling. And now I'm going to do the computation in let's say more the kind of parabolic notation. So I'm going to write this part as part of the elliptic operator. And this is divergence. So you have k times identity from here, or kappa times identity, and then minus delta to the 1/2 divided by lambda times h of x, t, and lambda x times gradient rho. Okay, where this h is related to w in the following way. So w is curl of some capital U in the fast variable. So curl. So just to recall, I'm calling this variable psi, and H is an antisymmetric matrix which represents the cross product with U. So H applied to some other vector, V, is the same as U cross V. Yes?
And it's also divergence with respect to X.
No, okay, yes, you're right. This is not the same as this one because the divergence would hit this one. This is the what you're worried about? Yeah. Okay. They're not the same. I agree. So this is not the same. So the remark of Vikram is that they're not the same. But at the end of the day, this is the. Let me think about this for a moment. No, in fact, okay. So in fact, what I should think about is that W is divergence free, so there's no psi here. So thinking about Onsager, and I'm not even sure you talked about this too much, when you have these, say, Mikado flows or any other flow, it's divergence free in the fast variable, but when you compose that with the, okay, so the model to think about, I will have to talk about this anyway, is that this W xt psi has the form of Mikado flows. So there's some AK xt times what Hyunju called this capital W, but these are essentially these functions supported on pipes, disjoint pipes, and it's in the direction of K, let's say. So this is a sum over a finite number of vectors. Okay, and divergence freeness in the fast variable means that we have this condition. Okay. But then I also want the W, when I put W of xt lambda x, to be divergence free, and that requires a corrector. And so there is usually a small additional term, W corrector, xt, which is small in terms of size compared to this term. This is sometimes called the principal part of the perturbation. And this is just there to make sure that this sum, whenever I put here lambda x, and consider this just as a function of x and t, is divergence free. One way to do that is to actually look at the vector potential of this. So in a sense, this W would be the W principal part, which is the Mikado flow plus the WC. Okay, so thanks for the question. So then, and in that case, then in that sense, this is equivalent. But this is only true if you really put the lambda inside. Okay, so maybe I put it, I don't know if this was clear. But anyway, I'm not going to talk about this anymore. I'm just talking about this one. Okay, so in that case, you can just say U, this capital U, is again a function of x, t, and psi. It's we can think of it as the vector potential of the W, and it determines this antisymmetric matrix in this way, and then that's the operator that I want to homogenize. Okay, good. Sorry for this, but thanks for the question. Okay. Now, the ansatz for the solution is already something that we know what it should be, so I can just write down the ansatz, and then I have to check things, but the ansatz is that it's of this type. The solution is given by some homogenized solution, rho bar, plus 1 over lambda, and then I have lambda x. This would be the solution of the cell problem, scalar product with the gradient. And then there is some other terms, which I'm just going to write all together like this. This would be the order lambda, 1 over lambda squared, and so on. But now I'm not thinking of a formal expansion. I want to say that's going to be my solution. So I'm looking for a solution of this type, which means for this one, we essentially know what equation it has to fulfill. So we know this. We have a formula for this, or at least we know what equation it has to solve. So this part is determined. And this has to then be determined by the fact that the sum has to solve the equation. And the point will be to just try to figure out some bounds on this that ensure that it's smaller than 1 over lambda times this term, okay? So that it really is a lower order corrector. That's the whole game. Good, so now I'm just going to do some computations. Sure. Yeah. Yeah, but not explicitly. So this dependence is really explicit. Here it's the same way as you wouldn't write lambda x here, even though it depends on lambda. But it's just, so once I plug in this form into the equation, I get an equation for rho tilde, and that's what I want to derive now. So of course, rho tilde depends on lambda, but not necessarily in this nice disjoint way. So just to compute and make you accustomed to my notation, if you compute so I want to get, rho tilde is what I want to plug in. And it's this difference where I know that, rho is supposed to be this solution. That's how I think of it. So I just compute the gradient of rho tilde and so on. This is identity minus the fast derivative when the derivative hits this times the gradient rho bar. And then there are terms of order lambda, 2 types. Second derivative of the rho bar times chi plus the derivative in x variable of the chi times gradient rho bar. Okay, and I'm not so in the computation today will be very computation heavy, and I'm not going to be very much concerned about what it means nabla and second nabla 2, right? It's just first derivative, second derivative. These are typically vectors, these are matrices, but this is okay. It's just important to know what number of derivatives. Okay, the time derivative has a similar form, minus 1 over lambda mixed derivative of the rho bar times chi plus 1 derivative of the rho bar times dt chi. So this dt and the dx are derivatives of the slow part of this perturbation. Okay, and now I can write down the equation for the rho tilde. The rho tilde will be a solution of the parabolic equation. So there's this part. Sorry. Let's call this term here, this one, this matrix, A tilde. Okay, A tilde is depends on x, t, lambda x. And I know it's elliptic, and the elliptic bound is the kappa. Okay, so I have a uniformly elliptic parabolic PDE. I can write down now the equation for rho tilde, and then I just have energy estimates. So the task is simple. I'm going to write things in this way. So you see, I've computed the gradient and dt, there's the dt, of course, and then the gradient enters inside the divergence multiplied by this A tilde. And so, for instance, you have like A tilde multiplying this term. So there's this term, A tilde times identity plus the transpose of the psi gradient of chi times, so gradient rho bar. And I'm going to already, looking ahead, subtract the average. So this is again an object which depends on x, t, and lambda x, or psi, okay? And I'm going to subtract the average in psi. I will have to put this back in a bit, but for now I just subtract it, and then this is multiplied by rho bar, gradient rho bar, okay? So that's one term. And then you have another term of order 1, which is including the dt rho bar. And then I have this. This is going to be my homogenized equation. So it's the psi average. So this, recall in my notation, this means average in the psi, which is always the periodic variable. So identity plus this gradient times grad rho bar. Okay. So far, I've just got this term, and I've added and subtracted this term. And you see here, this is going to be my homogenized equation. There's no more fast dependence, no more psi dependence. And then there is some additional terms of the type 1 over lambda. All these things that are here in the brackets and these ones, and there's lots of them, like divergence, A tilde, second derivative of rho bar times chi, plus A tilde, one derivative of chi in the slow variable times one derivative of rho bar. And this is still inside this bracket, minus chi dt grad rho bar minus dt chi grad rho bar. Okay. So the dt terms are just copying these ones. There's a dt here. And the other one is inside the divergence. So just to pause for a minute about this expression, is just a computation. So all I did so far was to make an ansatz, and I plug in that ansatz. Now, yes, what happened? No, it's part of this A tilde. Yeah, the A tilde has the kappa inside. Rho. Well, rho, you mean this one? Well, that one solves the equation. So I plug this in there, then there's no more rho. It's just rho bar or this term. And then the one that you're thinking is like the dt rho bar. For instance, here, when I take the average, there is, for instance, the average of this part, which is just the average of A tilde multiplied by this. Now, the average of A tilde, this drops out. This has zero average, but you have left with the kappa. So there's that term. Okay, so somehow the idea is to make sure that this is at most order 1 over lambda. Ideally, it should be order 1 over lambda squared, right? It should be the next order, if you remember from yesterday. So, and now I have that it solves an equation, parabolic equation with the right-hand side, where, for instance, there are things like this, divergence of something divided by lambda. So this looks kind of good. This would give me, by standard parabolic energy estimate, would give me a bound on the rho tilde, which has the 1 over lambda. So this is the key one. This one doesn't have a 1 over lambda. And you can think of this as the analog of the oscillation term in convex integration. That you have because you have things like fast times fast minus its average. You're hoping that so it has zero average. So this thing is fast oscillating. It still has fast frequency and zero average. But you have a divergence in front. And that's the whole point of Mikado flows in the convex integration, that when you have the fast derivative inside the divergence, you get 0. And so the point now will be to make sure that that happens here also. So this divergence has a fast part and a slow part. When it hits the fast variable, which would give me a factor lambda, that should cancel, that should be 0. That will give me the cell problem that we saw yesterday. And the slow one will have a 1 over lambda. Okay? So that's why I'm saying it's basically the same computation that I did yesterday, but I want to do it in a different way. So you see 2 different ways. Okay. Now, so let me compute this average. Show you the computation for that. We have this A tilde is kappa times identity plus delta lambda h x t psi. Okay, so this is a function, a matrix valued function of x t psi. Okay, and now this, let's say, homogenized coefficient, which is the average of this A tilde times the, what was it? Identity plus transpose of the gradient of chi. So I already showed how to start computing it. You have kappa times identity, and then you have, of course, this one times identity doesn't give you anything in the average. So the only other term that will give you something in the average is a fast times fast. Slow times slow gives you something non-trivial in the average, and the fast times fast. And that one here is this 1/2, for some reason minus, but maybe did I have a minus earlier? I think I put a minus here, right? Yeah, minus, well, it's this h times the gradient of chi. But okay, the h is like vector product by u. Okay, I have here a matrix, but with some slight abuse of notation, I can think of this as u cross that object, okay? So it means cross with each row, I think. So now let's concentrate on that term. So let's call that B. B is this thing minus its average. And the average is this A bar. Okay, so this has 0 average. This is a function again of B of x t psi, and in psi it has 0 average. Now, okay, so just to, at least the way I prefer this computation is to consider its what are they? The columns, B, E, J, for the coordinate vectors. This can be just written in this way. 1/2 over lambda, and then it's U cross EJ plus U cross gradient of psi j minus the average of this. Okay, it's just a computation. And so you see what I need to look at now is divergence of B times gradient rho bar, but keeping in mind that I'm not really thinking of this as elliptic matrix or whatever times gradient, because in the fast variable there is no dependence in this gradient. It's really the B that has the fast dependence. So that's the one I want to concentrate on. So I'm going to write this. This is really too little space. I'm going to write this as the divergence of B grad rho is writing, each component of this one hits one of the small bj's, one of the columns. So it's divergence of bj rho bar. And now, by just the product rule, this is divergence of bj times dj rho bar plus bj scalar product with gradient dj rho bar. Right? And now remember, it's the bj which has the slow and fast. So I can separate this term, this is the main term to worry about, into a term which has a lambda, which is the divergence in the psi variable. And then there is another one which does not have the lambda, which is divergence in the x variable. And then this one. Okay, so as I said, what I want is this to be 0. So this has to be, I can't use the fact that there is a sum and I can't use this. It's just a scalar number, depending on x. So this has to be 0. Sorry? Here? This one? Oh, divergence in x. This is an x. So here I'm thinking of partial derivatives. So not writing psi equals lambda x. I'm thinking of x and psi being independent variables, and I'm just differentiating in x. And here I'm just differentiating in psi. You see this bj is just this function. And here the psi and the u are functions of x, t, and psi. Okay, now it turns out, you can just, so what is the divergence in the psi variable of this? You do the computation, you get the cell problem. So divergence in psi of bj equals 0 is precisely what we already know, the cell problem for the chi-j's. Equals delta to the 1/2 over lambda wj. Okay, this is the equation I had yesterday. And yesterday this was a necessary condition coming from equating the coefficients. Now I'm going to show that it's also sufficient. So using the cell problem, which is the equation for chi-j, you can, well, here also, you can integrate by parts, right? This is an integral, this bracket means integral in psi. You can integrate by parts, and then get basically like the curl of u, which is w. So this is the same thing as what we had yesterday. I mean, it's a matrix with these entries, where again, it's average in psi. So now we are really back to where we were yesterday. And now the next thing, so solving the cell problem means this is 0. Nice. So, what is left is this part, this sum, and this is what I have here, right? So what I've done on that board is just evaluate this term. And I want to get a 1 over lambda. That's my goal. So since now having this choice of chi, which is the solution of the cell problem, now I have divergence in the psi variable of Bj equal to 0, and its average is also 0. It's a periodic function in psi. We can write Bj with a vector potential, curl in psi of some other vector, Cj, for some Cj, which again depends on x, t, and psi, and has a 0 average in psi. And then this Bj, okay, so again, since now this is a partial curl, only in the psi variable, so then when I plug in lambda x here, I have the usual kind of formula. I can write Bj as 1 over lambda times the total curl of Cj x. So now I write, I'm thinking of this as curl with doubling the variables, minus 1 over lambda times only the partial curl in x, Cj. So now it's like this. Okay, so this is a total derivative, like this one is a partial derivative. Right, so the way to think about this is just to evaluate this curl. And this curl, when it hits this one, it gives you this. And when it hits this one, it gives lambda times Bj. Okay, and then I multiply this by dj rho bar, and then plug this in here. I can also take a, sorry, what? Sorry? There's a J here, sorry? Yes, here, yeah, let's put a bracket. Yeah, here also. So now so now I can actually just go back to this formula. Divergence of Bj dj rho bar is, well, okay, you see there's product rule, but it's basically, there's this curl, for instance, so this part is already divergence free, and then there is a term with a 1 over lambda, so certain things cancel, and what you get is minus 1 over lambda divergence of gradient dj rho bar cross Cj. It looks pretty nasty, but it has a nice structure. These are the terms. Okay, so basically you have something like second derivative of rho bar times this Cj, or one derivative of Cj, but in the slow variable, times one derivative of rho bar. And so finally, we have the situation that there is the 1 over lambda. So we can write this equation for this corrector term. It has the form 1 over lambda times divergence of something, f. And let's see, so there was still some term which is not a divergence, but, okay, there was these dt terms, these ones. If you remember, there was this long computation. There's some terms which still have a 1 over lambda, but no divergence. Okay, they're a little bit annoying, but not really. And so where this f, capital F, is of the type, let's say, and the G also, they are also of the type that you have say, second derivative, some second derivative of the rho bar times either Cj or Kj, or first derivative of the rho bar times one derivative in the slow variable of the Cj or the Kj, all these terms. And also you can have dt. So one of these derivatives can be dt also. Okay? And then we just use the energy estimate. And so for instance, write it, so for instance, okay, let's forget about this one. It's not so nice, and let's just concentrate on this for now. So if I just forget that there is this type of term, here the energy estimate will be that, for instance, L2 norm squared plus kappa times the integral of the gradient is bounded by 1 over kappa lambda squared times the integral in time of the L2 norm of f squared. There is the 1 over kappa, which is the ellipticity, and 1 over lambda squared because everything is squared. And now, when I want to estimate what is f, so I need to know what is this norm of this type of quantities. Well, one of them, for instance, this one is something that essentially we already seen yesterday. It was the same type of term, except here now you have a second derivative. Okay, maybe I recall, it's too much blah blah without writing, it doesn't stop making sense. So yesterday's term was, okay, that's the first corrector. Maybe I write again. So rho is rho bar plus this term. Okay, so here we were saying the L2 norm is 1 over lambda L infinity of this times L2 of this, and this is all supremum in time. And now we have this term, and here I have an estimate of the type, let's say I concentrate on just one term. It's cherry picking, like Ujjwal is also just saying one term. Out of 100 of estimates, you pick the one that is easiest to explain. So that one will give me 1 over, kappa lambda squared, and then it's second derivative of, so there's again chi L infinity, and then second derivative of rho bar. I think that's probably correct. Okay, but so this will turn out to be the same order, because if you start looking at second derivative, even if it's under the integral, it's a little bit like first derivative. It will again, how is it? So I should put maybe a kappa here and then a kappa, extra kappa here. So then this term is the same order as this term. And what happened to this? This is a little strange. But maybe it's because I should also have chi squared. Yeah, I'm squaring everything. So this one squared, this one also squared. Yeah, I think that then it's okay, because then the chi, what was our estimate for chi? The estimate for chi was, I mean, this was essentially a question mark. It was wishful thinking that we have this. But that's the best one can hope for. And if I'm not completely mistaken, they should agree. There's still something with the delta. Now is the point to say it's an exercise, because now you have all the information to figure out. Anyway, it's just one term, and it's actually, I mean, I think Ujjwal was really concentrating on the difficult terms. Here I'm just saying this is the easiest term, in fact, because the estimates on chi, I said it's wishful thinking. This is the key difficulty in this part of the proof. This is okay. If I would replace this by P, it would be immediate from, say, Calderon-Zygmunt. The L infinity, you could show that it's still true by Moser maximum principle. The point is you have this drift term, right? We are talking about solution of this equation, okay? The maximum principle is still okay because I can more or less forget about this. But once I have derivatives, even though it's a slow derivative, I have to differentiate this equation. That x is a parameter in this equation. It's not a variable of the PDE. It's a parameter, but I still have to differentiate. And as soon as I do that, I get a derivative of the W. And I'm in big, big trouble. It's kind of like saying you have a, through x, parameterized set of drifts, even if there's no x dependence here. This one will mean that, you know, neighboring trajectories could diverge very quickly. It's fast, right? And there is actually, I think this was a key difficulty of Armstrong and Vikol to apply something like Mikado flows, because you have these different tubes. This drift pushes you very far away and you lose that kind of control of the chi. And they have an appendix where they give the argument, which is known in KAM theory, that you really have a problem. So this is a difficulty which I will talk about tomorrow. Okay, but if you don't worry about difficulties, it looks actually good. And I am sorry, I'm missing a delta somewhere, but it's a good exercise. Okay. Yeah. Now, but I want to talk about another difficulty in the remaining time, which, okay, so let's say, there are two more major difficulties that one has to think about. One is that I was doing the computation in this model problem where there's no macroscopic flow. So I was doing the computation for homogenizing this double delta to the 1/2 W dot grad rho equal kappa Laplacian of rho, okay? But what I really should be looking at is this one. Once you have this sort of macroscopic drift, you quickly realize, so you can run the whole thing, the whole, what I did yesterday, the multi-scale expansion, or you can try directly something like what I did today. You will quickly realize that the only way that this method can work is if this chi has the form, it depends on x, t, and lambda times phi of xt, where this phi is the inverse flow map of u. Ujjwal called this psi, but I'm using psi for something else. So, but this is the inverse flow map. Okay, once you have an inverse flow map there, of course, all these formulas get much more unfriendly. But it's okay. That's not a big difficulty. However, the big difficulty, as it is in Onsager, in any intermittent or non-intermittent, is that this flow has very bad properties over a long time. So it has a kind of characteristic time scale where you still have good control over that flow. I mean, that control over the flow means controlling the derivatives of this. Of course, you start to have derivatives all over the place. You need to have good bounds on them. They are good for very short times, which is proportional to the inverse of the Lipschitz norm of this, like lambda, or delta to 1/2 times lambda. So then you have to cut off and restart, cut off, restart, cut off, restart. That creates problems. And one big problem is the following. So it means that even if you are able to do this homogenization, so you get this A bar, which was the, from the kappa, from the small kappa to a bigger kappa for the homogenized solution. It's only valid on these short time intervals, and in between there are other time intervals where you haven't done anything. The W is 0, so there's no improvement of the ellipticity. Okay, so it's not like you've improved the ellipticity for all time from a small ellipticity to a bigger one. It's only like half the time. And that has to be addressed. So these are the two problems. The fact that you have to deal with the flow, inverse flow, and then you have to glue these different flows together. This can be solved, roughly speaking, by the same tricks that Hyunju didn't explain, but Vikram will. You have these cutoffs, you have cutoff functions, you have characteristic times, and so on. I would say it's laborious, but I mean, they're not such big new ideas. But you need to do something non-trivial in this other problem. So roughly speaking, the general plan of how to pass from the equation for Q plus 1, the non-homogenized one, to the homogenized one is the following. So here is the non-homogenized at level Q or Q plus 1. And I want to end up with, maybe I use more boards. I want to end up with this one, the same equation for Q. Okay, so it's what I was explaining yesterday. You have Q going from 1 to infinity when you define the vector field. So you have U Q plus 1 equals UQ plus WQ plus 1, and this has the form of that W, and this would be the UQ. So I have this homogenization methodology, but there are several steps. So the first step is actually to deal with this. This is sort of, let's call this Lagrangian shift. I have to essentially change my coordinates into the coordinates that the particle sees that is moving with the flow of UQ, okay? Because then the UQ is somehow not there anymore. I'm just with that flow. And I can basically treat it as if it was not there. Okay, so that will also change some things. So let's call that solution rho tilde. And I'm going to put a bar here. It's not that it's not there, but it's I'm going to put a bar. The U with a bar and the U with a non-bar is another thing which I don't know if Camillo will explain it. But when you do this gluing, you have to change your solution to being a solution of Euler on small time intervals. There's a difference without talking about scales even. Okay, and then this ellipticity is going to turn into something that I've just looked at, matrix. This is an easy step. Next step is the homogenization, which I've just tried to explain in very briefly. Homogenization, where I'm going to end up with a UQ1 plus UQ bar, sorry, rho Q1. Sorry, right, so here, of course, this has the WQ plus 1 inside this term. Okay, so this is fast oscillating, but now I get to an equation which doesn't have a fast oscillating term. And it's still, okay, so this is the bar. Let's so call it Q. Okay. So that's the step that we essentially just seen. From this one, in the next step, I can see that this term will not be diagonal, but the non-diagonal terms are very small. I mean, I started with essentially something that was diagonal. This had this term which was antisymmetric, but I will also try to show you that when you use Mikado flows of that type, you get exactly the diagonal, and then there are error terms. So remove those. So remove non-diagonal. And this will end up in an equation where it looks like this. Divergence of kappa q tilde, which depends still on x, t, and x divided by tau, or some times k tau, sorry, t. Yes, x, t, and t divided by tau. I will say more about this in a minute. So this is what you get when you apply homogenization using essentially the technique that we need to use for the Onsager conjecture. And now we need to do a time averaging. So I need to replace, because this is still oscillating, but not in lambda anymore. The lambda was removed at this step. So it should be lambda q plus 1. Okay, was removed at this step, but there is still these time intervals. So there are two scales in time, let's say tau q, to get to something where it doesn't depend on anything anymore. So I get to it's actually kappa q plus 1 plus kappa q. And then, okay, this one is much smaller than this one. So this can be removed without any cost. But I still need to work to replace this U bar, which is the one solving Euler, to the original one. So there's a final step which is related to the gluing. Okay, so I showed you this step. Now I want to talk a little bit about this step. Yep. Yeah. The time averaging is only needed because probably not. Yeah, probably wouldn't need it. The problem is still you have to deal somehow with this flow. Right. So it's not just the construction of the U that gives you this problem. It's that you have this in the cell problem. You have this flow. So as long as you use this, you have to do time cutoffs, and you can't. I mean, I don't think you can have it times intersecting, and as soon as they don't intersect, you have times in time intervals which are essentially of the same size, where nothing happens. Why can't you have them intersect? Well, because, okay, you can't have them okay, so philosophically you can't have them intersecting because this gives you a change of variables in the cell problem. You're changing into Lagrangian coordinates in the cell problem. If you have them intersecting, what are the new Lagrangian coordinates? This one, I mean, this is needed so that in the cell problem you don't have this U. You don't have this term. Yeah, I mean, okay, I mean, it's an ansatz for a solution. As I said, the solution is unique. I have to guess what the leading order term is. And the problem is if this U remains inside the cell problem, it doesn't depend on the slow variable, so it looks like a constant drift. But depending on x and t, all the estimates are out of the window. So I think even if you have a method to avoid the time cutoffs needed for the Mikado flows, you still have to think about this. But the time averaging works, so it's not, you don't have to work too much to avoid it. It's possible to do it. And okay, so I just want to give a sort of simplified setting for this time averaging. Because this is something, again, it's like homogenization, but just for a fast in time oscillating ellipticity coefficient. And I've not really seen this in the literature. So I should also say Armstrong V-call have to have a step like this as well. And what they do is it inspired our work, but we had to be more precise. We had to really get the optimal estimate. So let's say I'm looking at an equation of the type u dot grad rho equals some kappa tilde t Laplacian of rho. So I'm ignoring this. Yeah, so maybe I should say t divided by tau. I'm ignoring the xt dependence. And I want to compare this. Okay, and this kappa tilde has the form of t is kappa 1 plus kappa 0 times some positive oscillating function of type tau to the -1 times t, where I have a kappa 0 and I have a kappa 1. And of course, this is non-negative. Let's say it's periodic with average 1. So I see it's important already at this step to ensure that, you know, there's always some, sorry, I think it's, yeah, no, it's okay. So there's always this ellipticity. This is I'm thinking of this as the smaller one. And since the average of this is 1, I want to converge to the average, which is kappa 0 plus kappa 1. And then it's helpful to think of, so another way to write this kappa tilde is that it's kappa plus kappa times a of t divided by tau, where a is a function of average, periodic of average 0. So the average is kappa, and but okay, this, of course, this expression has the disadvantage that you don't see that whatever value of a you happen to have, it's always still uniformly elliptic. And so I want to compare this equation to the equation. I'm not being very well organized on this. So yeah, just delete this. To this one. this is the average, right? I want to converge, I want to say that the leading order term in the dynamics of this equation for the rho is this rho bar. That's what I mean by comparing the two equations. I want to get an L2 bound on the difference of rho and rho bar. Now, what can you expect out of this problem? This is still, okay, it's a function of x and t, and everything is smooth here. But what can you expect? The key point to notice is that in this equation, well, with this tau especially, you have two different time scales. There is the time scale given by the drift, right? So the typical, the advection time scale is 1 over the Lipschitz norm of u, or L infinity norm of the gradient of u, right? That's the typical time scale. It's called in turbulence eddy turnover time. This would be the time that is used also in convex integration. It's delta q to the 1/2 times lambda q, or the tau q. And there's another time scale, the oscillating time scale, is this tau. So without even doing any computation, one has to realize that the only way you can expect a proximity of this equation to this equation if this time scale is smaller than this time scale. This has to be fast, and fast means fast compared to the slow dynamics. So, so expect sort of time homogenization only if tau times gradient u in L infinity is small. In fact, this will be our small parameter. Now, and then how to obtain the result? Well, we have to basically cook up analogous to this multi-scale expansion, cook up an approximation scheme to the oscillating equation, starting with the non-oscillating equation, right? So previously we were saying, okay, I'm looking for an ansatz for rho. It's rho bar plus correction terms, okay? Here it's not so clear what would be the good parameter to take. You can try tau, you can try this, but the simplest one, which is also what Armstrong and Vicol used, is to say, well, I just put terms which are given by successive approximations. So I think of this as a limit of, you know, these tildes are the differences, these are the better and better approximations, and they are supposed to be solutions of dt plus u dot grad equal kappa plus kappa a t divided by tau Laplacian I minus 1. Okay, so I start with this one being rho 0. This is rho 1, and so on. And you see rho 0 is just a solution of the homogenized, and then it's you know, the usual method of success. This is my kind of error term. So I just have I minus 1. And for the differences, so if I have tilde is the difference of successive terms, these are the terms that should go to 0, then it's the same equation. You just subtract two of these equations. It's linear, so it's, okay, maybe I write capital dt. The capital dt is the advective derivative. It will never be anything else than this one. So, it's this. Okay, and another notation where I'm going to call this a tau of t. So these are with the tildes, equations, and then they have 0 initial data. Differences have 0 initial data. Okay, and the goal, this is what, or let's say claim, is that the energy estimate for these looks as follows. Gradient. Is bounded by tau times gradient u in L infinity to the power 2i times d, where d is the dissipation of the rho bar. So this is kappa times gradient rho bar, L2 squared. Okay, so you see the higher approximation, if this is a small number, gets better and better. That's the estimate. And the proof is essentially just energy estimates, but it's not, I mean, at some moment you have to use averaging. So I want to show some details of this. Let's see how much I can show. And there are certain assumptions that are, I mean, additional assumptions that I need to be able to derive this. One of them is that, of course, you can always expect that you will have some information on the initial data appearing in the estimates, the initial data of the rho bar. And one of the assumptions is that this d is not too small compared to the initial energy. So assume that d bounds, let's say, like 1/2 of the initial energy. You see, we have the energy equality for the rho bar, which is at something, I mean, some value. So that the energy at time t is equal to the energy at time 0 minus d. But you want to consider times where there is already some dissipation that happened. This is also sort of natural, at least with hindsight, because you can't expect any sort of homogenization in time if you don't wait long enough. And the time has to be sufficiently long compared to, you know, the kappa actually having some effect. Okay, so right. So from this claim, then it's easy to derive that okay, rho minus rho bar L2 squared is bounded by this squared. This is going to be enough for the rest of the iteration. So just to compare, I think Armstrong V-call have a power 1. That's, if I remember correctly, the difference in this part of them. Now, in order to get, and it's actually, it's a pretty complicated inductive way of obtaining energy estimates. And at least I want to illustrate why it's complicated. So I'm going to call, okay, just some notation. I'm going to say this norm of rho n will denote essentially the energy norm. So it's, okay, I'm going to write like this. Nth derivatives in L2 squared, supremum in time, plus kappa times the n plus first derivative squared. And because we need to sort of keep track of the dissipation rate, I'm also going to add this term. I'm going to say something about this soon. But there is something, so just to compare, let's say this term to this term, I mean, this one appears already when you have, say, like 0 here, right? So why do I put it here? I put it here because this kappa times this integral is the dissipation rate. And I will need to keep track of that. And in all of these estimates, it's good to think about different scales. So it's sort of clear that when you compare this expression to this expression, here I have one derivative squared. Here I have n plus 1 derivatives squared. So in order to make sure that they are dimensionally consistent, I need to multiply this one by the inverse of length scale to the power 2n. Okay, then they have the same. Right? The dimension of this is, just looking at the number of derivatives, 1 over L to the 2n plus 1. The dimension of this is 1 over L squared. So you see, I need to multiply this by 1 over L to the 2n. And this has that dimension, right? Because kappa has dimension, what is it? It's L squared over T, length squared divided by time, and the gradient U in L infinity has dimension 1 over length. Okay, so you have 1 over L squared here. So at least dimensionally it's consistent. This is always useful because when you have this kind of estimates, you get something, you use Young's inequality, you use interpolation. It's easy to make mistakes. You have to get something which is dimensionally consistent. I'm not going to get very far. Just to prepare, one more thing. So when you look at this kind of equation, to get an energy estimate for higher derivatives, you need to differentiate, which will give you this commutator. You have to differentiate the U. So just to have this in mind, note that, okay, there is the following. So this commutator applied to some function, f, in L2 can be bounded by the first derivative of the U times n derivatives of f plus n derivatives of U, first derivative of f. Okay, just by interpolation. You have the product rule, lots of terms, but all of them can be interpolated into these two, and then Young. So this is something that you have to use repeatedly in this derivation. And now, okay, let's just see how to start. So the first one, the rho bar, is nice. Maybe I even skip the details of this one, because the rho bar has just the standard. There's no oscillating term in the rho bar. Okay, I've just erased it, but it has no oscillating term. It's really just straightforward energy bounds. So the bounds for the rho bar, so remember rho bar is the rho 0, the 0th order approximation. It will be bounded by initial data in Hn. Of course, it's Hn energy estimate squared, plus, and the other term is precisely of this type, to the power n times d. And now, okay, another thing that is good to assume, and that's something I will have to deal with later, is that the initial data, and this is, this is something that's also growing along the iteration, right? This is like delta q, so the 1/2 lambda q divided by this lambda q, kappa q. This one is, let's say, lambda q to the 2/3. This is lambda q to the minus 4/3. So we're speaking about a huge number here. So just to say, this should dominate this one. Okay. It's a pretty harmless assumption. We can drop this in later purposes. Okay, now the estimate for the first approximation, first corrector. So now this has this equation. Initial data is 0. So I can just use, okay, let's say first we compute this norm, the 0 norm. Okay, so just the standard L2 estimate, which looks like this. Right, so this is bounded by this multiplied by, sorry, this is 0. Right, so this one is actually the same as that. So maybe I should have put rho bar. Right, I'm multiplying this by the test function. It gives me a bilinear term, kappa, and then there is this A tau gradient 1 gradient rho bar dx dt. Okay, and now we come to the averaging. So far it was just energy estimates. I didn't do anything. But here you see, you have this fast oscillating, this A tau, remember it's A of t divided by tau. A has 0 average, it's oscillating. Let's think of just sine of t. So I can write this as d dt of tau times the primitive of A. Let's call it capital A. Okay? So this one looks like this. It's d dt of something. Integrate by parts in time. Now, if I do that, what I will get is, so first of all, I can replace d dt by dt. It doesn't depend on x anyway. And then integrate by parts. That has the advantage that I can use then the equation of the rho tilde 1, is this one, or of this one. So you get a bunch of terms from that. I don't think it's so useful to see all of them. No, only t. Yeah, this was maybe too fast. So it is d dt, but this is the same as d dt plus u dot grad of this term, by the stupid observation that this doesn't depend on x. And then I integrate by parts, then you're right, and then I integrate by parts in x and t. But it's just to have the capital D. Of course, I could also not have it. First, just integrate by parts in d dt, this d dt, and then smuggle in the u dot grad because it's a full divergence, so it doesn't affect. Okay? But then, of course, I have the d dt here. I want to put it inside to use the equation that gives me commutators. So the whole thing is a bunch of computations. And yes, I don't think it's okay. I mean, it's not that it's not important to do this, but I think it doesn't help if I do it. You should do it. Then you see. So that's what one gets. And you see, compared to this, okay, you see, this would be the case of n equals 0. So if n equals 0, then this term is not here. I just have d. What I'm losing is this term. It's somehow more derivatives, right? I get more space derivatives when I do this. clearly, because I have kind of already one derivative. Imagine you have the ddt, you replace it by the equation, you have gradient times Laplacian, you have 3 derivatives. Okay? So in fact, yeah, maybe it's, before coming to this step, it's useful to see that an intermediate step, which has this form. It's the rho bar 2 norm times the 0 norm of the rho 1 plus kappa tau squared. That will require doing this trick once more on this term times rho 1, rho bar the 1 norm and the rho bar 3 norm. Okay, and on this one, I use Young to absorb this on the left-hand side. Okay, and then you see you have again a term of this type where you have this kappa tau squared. And we have this squared as a loss because we have more derivatives. Okay, maybe I stop here now and continue tomorrow a little bit just to see what is the pattern. But I think I basically gave you all the ideas of how to obtain this. Maybe just one comment where it becomes nasty. So, for instance, okay, this is the row 1. Suppose I do it for the row 2. For the row 2, I do this. I get terms with the row 2 and the row 1. So you have this kind of bilinear term. And in general, you have all of, you need to basically know, for instance, if I write the equation, I integrate by parts. I use the equation for the rho tilde 1. It involves, rho tilde 2. The rho tilde 2 would be with a 2, 2, 1. So out of that, I get one term which has a rho tilde 1 times this rho tilde 1. So I need to deal with that type of term as well. And the pattern will be that any integration by parts leads to some terms which you can directly estimate by the energy norm, plus some bilinear expressions involving different ones of these rho tildes. So I will need to have a bound on all of them. And that can be done by induction, but okay, it takes some time to actually figure out the details. Okay, so I would not say it's a nice exercise, it's a tedious exercise, but I wouldn't say it's worthless to try. So yeah, so I think, I don't know. I mean, if you want to see more, I'm happy to say more about this tomorrow, but I think the idea is sort of already what I presented. Okay, thank you for your attention. Mm-hmm.
There do you use the fact that the U bar was defined? So do you need this time averaging there as well?
No, not the time averaging. The gluing is so for the gluing, maybe I should say a little bit for the people who don't know. I hope it's okay. Just a couple of minutes just to say what this gluing is. So there are these small time intervals and there's this problem with the flow, but essentially the gluing is when you go from, in Onsager, so this is the gluing of Phil Isett, which was introduced in his paper. So here I start with, let's say, essentially, I have my approximation. And I want to replace this by an exact solution of Euler. Plus, okay, different pressure equals 0 with U bar at some fixed time the same, okay? So there is some fixed time intervals, these short time intervals that I fix, and on each time interval, there's on the, let's say, one point of the interval, I pick the value of UQ, and I just solve Euler with that initial, that as being the initial data. And then I have to glue these together by cutoff functions. But the problem that Vikram is asking already appears without speaking of the cutoff function. When I do this in my so now I want to do the following in the advection diffusion equation, which is, let's say, advected by this one. I want to replace it by the one advected by this one, and I want to show that the solutions stay close together. Now that I mean, the question is the following. So these UQs and the UQ bar have a vector potential. This is ZQ. This is ZQ bar. So for the equation of the difference, if I have dt, say, rho Q bar. Let's say that this one is the solution to UQ, and this one is the solution to UQ bar. But they have the same ellipticity kappa, okay, kappa Q. So the difference is something that you can put in the divergence. So say you take one of them. I don't think it matters which one. It's just a question of the sign. So then you have something like kappa identity, where this is the kappa Q, plus, like when we go to this parabolic setting, you have something like ZQ minus Z bar Q, cross, cross, okay, so times the gradient, okay? So you have this difference. I mean, sorry, this one is the same. Wait a second. Am I doing something? UQ bar. Okay, I'm getting a little bit mixed up, but just not to confuse you. So the difference in being UQ or UQ bar amounts to a difference like this, which is compared, I think it is this one, which has to be compared to this kappa Q. Now, this difference is small because the difference between the UQ and UQ bar is given by divergence of something small. This is the size delta Q plus 1. So you can kind of expect that the difference ZQ to ZQ plus 1 is like RQ, size delta Q plus 1. And that is sufficiently small to absorb in this. Okay, I think it's actually even divided by lambda Q. Okay, I have to do the computation. But the fact that there's this small difference inside the divergence, you can try to figure out what is the equation for the ZQ and the ZQ tilde, the ZQ bar. There's a tau Q, okay, you have it by heart. What? Tau Q times delta Q plus 1. And I think this one is sufficiently small to be smaller than this. Yes. It's not essential. It makes things a little bit more complicated. So that one gives us something like xt dependence here with these squiggling stripes. But luckily, so we can, okay, we have to just adjust these stripes and all the setup in such a way that, of course, we don't do any homogenization in X or anything. It's already slow. But okay, the average, so let's say here I have xt. It's a really stupid trick. This property still holds independently of x and t. Okay, here you have still x and t. I've averaged in this variable. Once I average, I don't see this dependence. Part of that is already used in the way the stripes are constructed to keep the energy at the level that you want to reach. Here we use it in a slightly different way to make sure, okay, so we have to keep this xt dependence. This is representing these stripes. But when we just average on the fast time, we get constant values.